Welcome everybody, and now I am going to be talking today about a very famous model in interacting electron theory, and it's called the Hubbard model. Actually, this model was independently introduced by people like Kanamori, Gutzwiller, besides Hubbard, but the name Hubbard stuck. And incidentally, Hubbard model is a special case of another model called the Pariser-Parr-Pople model, or the PPP model, which was introduced in 1953. It was Pariser-Parr-Pople model. This was 1964, I think. And this Pariser-Parr-Pople model is a includes longer range interactions. So let us come to what the Hubbard model is. So the Hubbard model is a single band model. What it means is that only one orbital is considered per site. And electron-electron repulsions are taken to be non-zero only when two electrons are on the same site or same orbital. Or orbital. I can use interchangeably orbital and site because I am only considering one orbital per site. What we consider is only one repulsion integral, which is called U, which is given by phi I star 1, phi I star R2 E squared upon R1 2 is a double integral over two particle coordinates, phi I R1 phi I R2, because these are all vectors, d cubed R1 d cubed R2. This model was developed to understand ferromagnetism in metals, actually magnetism in metals. Well, because they are metals, the d by Hückel screening length is very short. And these people actually cut down the range drastically to just on-site interactions, Hubbard, Kanamori and Gutzwiller. So Hubbard's model hence restricts electron-electron interactions to same site. Of course, the moment you have electron-electron interaction in 3 dimensions, you cannot have an exact solution. No exact solution exists in 3 dimensions, but you have exact solution in 1 dimension. By a technique known as the Bethe-Ansatz technique, which we will not go into. There are approximate methods. Most celebrated was the method of Gutzwiller. Method of Gutzwiller, which is called a Gutzwiller variation method. What it does is the following: use the band solutions, the band orbitals, and write down the Slater determinant corresponding to band orbitals. So this is only in principle. So what you do is you write down the slate this thing. For example, if it is just a hydrogen molecule, the molecular orbitals replace the band orbitals. So it is just sigma 1s and sigma 2s, and then you expand the Slater determinant in terms of atomic orbitals. Once you expand it in terms of atomic orbitals, then so now we can define Slater determinants in atomic orbital basis, which are covalent or with one doubly occupied site, or two doubly occupied sites, etc. So in other words, what I am saying is that the many body band state can be written as C0 psi 0 plus C1 psi 1 plus C2 psi 2, etc., etc., where C0, C1, C2, these are all actually vectors with a coefficient for each covalent state or Slater determinant. That is because what happens is that you can have, when you have more than two sides, then you can have many different covalent states corresponding to different spin configurations. So that is the reason why C0 will correspond to many different covalent states, and psi 1 is similarly is a vector with a coefficient for each doubly occupied site. Site and so on and so forth. Okay, so you can have C2 similarly defined and so forth. In other words, what we are saying is the following, that is, in the hydrogen molecule case, for example, if I am going to write it, then I have psi of the hydrogen molecule, I can write it as C0 times the hydrogen covalent bond plus C11 times H plus H minus plus C12 times H minus H plus. So 0 refers to 0 double occupancy, one refers to 1 double occupancy. So similarly, when I have say n sites with n electrons, that is a half filled case, then for even n we have 0 doubly occupied site, 1 doubly occupied site, 2 doubly occupied sites, etc. Up to n by 2 doubly occupied sites. And these will have coefficients given by C0, C1, C2, Cn by 2. Now what we will do is we will construct a trial function which is a Gutzwiller trial function, and let me call it as something that depends upon g, the Gutzwiller variable. Okay, this I will say is nothing but C0 g C0 times psi naught, which is the singly occupied some completely sorry C0 times psi naught, because there are no doubly occupied sites. I can just write as C0 psi naught plus g C1 psi 1 plus g squared C2 psi 2, etc. So which means that whenever g is a Gutzwiller variable, and 0 less than g less than 1, when g is equal to 0, we get back the non-interacting state, rather when g is equal to 1. We get back the non-interacting picture. When g is equal to 0, we get completely magnetic picture, although not really magnetic, because g can never be strictly 0. Okay, because you will always, if you want to have magnetism, then there must be some admixture of the ionic sites through a virtual excitation. So this is completely magnetic taken with a pinch of salt, because it's not really completely magnetic, but you can assume it is completely magnetic state. And for 0 less than g less than 1, we have a correlated picture. So g, we can treat it as a variational parameter. G can be treated as a variational parameter. And we can minimize E of g is equal to psi g h psi g divided by psi g with respect to double occupancy. That is a Gutzwiller parameter. Well, for this we have to make certain approximations to the transfer terms, make approximations. I will not go into those. And the upshot is the following, that is, it was shown that there is a critical u below u which is uc, such that g is equal to 0 for u greater than uc and g not equal to 0 for u less than uc. So this is actually an insulator, and this is a metal, because you require double occupancy if you should have a metal, and if you have an insulator, then you need not have any double occupancy. But this has to be taken with a pinch of salt, because not entirely correct, as G is never 0 for any finite u. And any small t by u, which means that you always have doubly occupied sites, and that is the reason why you will have an antiferromagnetic interaction. Okay, so this was basically the Gutzwiller model, and this was pretty important, and nowadays you can use the Gutzwiller wave function. People try to do quantum Monte Carlo simulations. To study the Hubbard model using a variational Gutzwiller procedure. Well, we will not go any more into the Hubbard model, because solution of that has, there have been many papers on Hubbard model of various kinds, the single band, the multi-band, and so forth. But the most important thing to see is that the Hubbard model, although introduced for understanding ferromagnetism in metals, cannot give a ferromagnetic solution. At least for the single band model, except in some pathologically doped case. The pathological doping is that the number of electrons should be equal to number of sites minus 1, and the dimensionality should be 2 or greater. 2 or greater. And this is known as the Nagaoka theorem. What we shall do now is to understand the physics of the Hubbard model in large correlation limit. So, let us understand the physics of Hubbard model in large u by t limit. So, for this what we will do is we can use a simple dimer that is 2 hydrogen atoms. We can use a 2 hydrogen atom system. So, in this case, and we also use the band term or the hopping T term as a perturbation, and the unperturbed Hamiltonian is the interacting Hamiltonian. In this case, what happens is that for two hydrogen atoms, we have 6 possible states at half filling. What are those? We can have H up, covalent state, put it H down, another covalent state, then a state which is 1 upon root 2 H up, H down plus H down, H up, and then I can have a fourth covalent state which corresponds to H up, H down minus H down, H up, and then I can have two ionic states. The ionic states are H plus, H minus, and H minus, H plus. So these are the 6 states that are possible. When U is very large, the eigenvalues of these states, eigenvalues of H0 for these states is 0, 0, 0, 0. All the covalent states have 0 double occupancy, and so no U term, and then the others are U and U. The singly ionic states are having this thing U and U. Well, let us see how we go from here. So if I were to draw my energy scale on this, then I have 4 states which are all at U equal, which are all at 0 of energy, and then 2 states which are at U of energy. And these are HH, and these are H plus, H minus, and H minus, H plus. So the states that I wrote down here, these 3 are triplet states, corresponding to Ms equal to plus 1, Ms equal to minus 1, and Ms equal to 0. This is a singlet state, and of course these two are obviously singlet states, because in a single orbital they have got 2 electrons and the other orbital is empty. So these are also singlets. So here you have a degeneracy of the singlet and the triplet states. All of them are having 0 energy, and these 2 are singlet states. Now what I will do is, I will turn on the transfer term. The transfer term actually hops 1 electron from one of the sides, like H plus H to A, from this hydrogen to this hydrogen or back. So that is a transfer term. So what happens in the ground state? So what is the first order correction? So you have psi covalent, the transfer term, and the other one is also psi covalent. In other words, this is a first order correction. Okay, and psi covalent is what? That is HH, forget the spin for the time being, H transfer, HH. So whenever the transfer term operates upon HH, it gives me with some coefficients H plus, H minus, and another similar coefficients. See, let me say C1 prime, H1 minus, H2 plus. Given this, what happens to E1? E1 will be C1 times HH H plus H minus plus C1 prime times HH H minus H plus. So, what we are seeing is that this is covalent, this is ionic, which means the electrons are in different orbitals in the case of HH, but both electrons are in the same orbital in the case of H plus H minus or H minus H plus. So, they are obviously orthogonal. So, these are orthogonal. And they go to 0. So, the first order correction in energy E1 is equal to 0. So, we can only have a second order term, and second order correction is HH H transfer H plus H minus times H plus H minus H transfer HH divided by E of H plus H minus minus E of H comma H. This is one term, and the second term is HH H transfer H minus H plus and then H minus H plus H transfer HH divided by E H minus H plus minus EHH. So, when we are looking at this matrix element HH H transfer H plus H minus is non-zero only for the singlet state. Because you cannot hop an electron from one hydrogen atom to another hydrogen atom if the electrons are in the triplet configuration. The spin configuration is triplet, because if it is up and up you cannot hop, if it is down and down you cannot hop, and you cannot also hop if it is up down plus down up. So, only when it is in the singlet configuration you can hop it, and the value is for singlets, this value is just T. And as far as the denominator is concerned, H plus H minus has an energy which is equal to U, and EHH has an energy which is 0, as we see from this diagram. Okay, so this is the diagram that we have seen. So, what it means is that the singlet is stabilized by an energy 2T squared by U. Okay, just one second. So, this is actually minus of this, because the lower states are always stabilized. In second order perturbation theory, the excited states always stabilize the lower lying ground state. So, but the triplet states are unaffected. So, if I were to draw this diagram on this, what happens when I turn on the T is the following. The triplets will stay where they are, and the singlet will come down in energy, and this energy difference is 2T squared upon U. This is the singlet and these are the triplets, and these energy levels we are not worried about. because it is a very large U limit. So, those excited states are not accessible and we will not worry about them. So, the low lying singlet and triplet are split and triplet are split, and this splitting can be, this can be shown to be eigenvalues of a spin Hamiltonian. What is a spin Hamiltonian? I have H, let me call it KIN, kinetic. I will tell you why. This is 2t squared by u times S1 dot S2 minus 1/4. So, S1 dot S2 minus 1/4 operating upon a singlet, which is what I have written as a line, will give me minus 1 times the singlet, and S1 dot S2 minus 1/4 operating upon a triplet. I have shown the triplet by an arrow. So, this will give me 0 times the arrow. So, you see that this has created a gap between the singlet and the triplet. Singlet is a ground state. So, why is the singlet stabilized? The reason why it is stabilized is easy to see. That is, where I have 2 hydrogen atoms and I have an electron. I am just showing this is not a singlet, this is actually ms equal to 0, but assume it is a singlet, and then this can actually, electron can hop and I can get H plus H minus, and it can hop back and it can get another configuration whichever you want, H, etc., etc. Okay. So, which means, which implies that the electron can be delocalized between the two sides. So, one knows that delocalization always lowers the kinetic energy or it stabilizes. So, the state becomes stable. Now, in the case of triplet, of course, you cannot do this, because when I have H up, then you cannot have H plus H up, because Pauli exclusion principle does not allow it. Forbids this. So, this mechanism of obtaining antiferromagnetic interaction is due to P.W. Anderson and is known as Anderson kinetic exchange. Before Anderson showed that you can have antiferromagnetic interaction through this route, people did not know how antiferromagnetic interactions arose in systems. So, that way this was the first demonstration of how an antiferromagnetic interaction can arise in systems. So, what I will do is I will continue from here in my next lecture, and I will stop at this point. So, we will meet again. Thank you very much.